Assalamu alaikum, everybody. So we are back with the fourth chapter. Let me show you what this chapter is about. This is about probability, and as feared the most by students, the topic is at the basic level. It is comparatively simple, so you shouldn't um, be having a hard time understanding this topic. So please remember, this is introduction to probability. Now, probability is something uh, that in common language we talk about, that it's the chance of something to happen. What are the chances of different things happening around us? Now, mind you, this can be applied to everything and anything in life, like the health situation these days. uh, the corona has hit us badly. What are the chances that you stay safe till the vaccine arrives, or your family stays safe? Or what are the chances, God forbid, if you catch the disease, what are the chances of your survival, or what are the chances of mortality? Now, this is something that relates to health, but at the same time, we can think of applying this concept to our education, like what are the chances of your grades in this semester, especially in the circumstances that the university is closed right now? What are the chances that you get a good grade? Similarly, you can think of applying this in business. If you've started a business, what are the chances that it makes money in the first year? Uh, what are the chances that you buy a second hand car and it sells at the same price? Or maybe it gives you a profit, or maybe it gives you a loss. So these are some of the things that where you can think of applying the probability, and you can think about the probability. Now, what actually probability is measuring uncertainty in numbers. That's the numerical measurement of uncertainty. There are many ways to do that, and there are many ways to compute probability, but it is about the likelihood that you want to measure about some event that is going to happen after some time. So let's see how this goes. I'm strictly following the book here, so you should read the book carefully with it. Let's see the first slide in here. As I've told you, that probability is a numerical measure of the likelihood that an event will occur. Now, what is likelihood? What is likely? Something likely to take place, or something not likely to take place? Now, uh, if I ask you the simple question, how likely it is that your university opens after a week? Naturally, it is not very likely right now. So the chance is pretty low. And how likely it is, hopefully, by September, we open with a new session. So that's more likely, maybe, but still not certain. So probability could be something totally unlikely or something impossible. So the probability for that is zero. The probability of a certain event is one. If something is sure to happen, the probability will be one. And zero point 0.5 is a middle point. So if we say the probability is 50%, then the chance will be 50-50 of something to happen. So this means probability is actually a number from 0 to 1, or 0% to 100%, or zero point 0 to 1.0 maybe. Okay. Um, how can we think of applying this probability in business? So just take a look here. I mean, if you see what are the chances that the sales will decrease if we increase the price, that's a typical question usually that is asked of managers in business. Um, will your sales be stable, or will they decrease if you increase the prices? What is the likelihood that a new method of assembly will increase your productivity? Can you produce more? And what is the chance for that? And how likely is it the project will be finished on time? So many uh, public projects or private projects, we are very conscious about them, that we want to finish them on time, like your student project, maybe you usually get 4 to 6 months and you want to finish it on time. So what are the chances that you will finish on time? And what is the chance that a new investment will be profitable? Not all investments, they can't be guaranteed to be profitable. So the chances are they can be profitable, they can be in a loss, or maybe they break even. So these are some of the situations where probability could be um, thought to be applied in a business scenario with most of the managers. So as I've told you, that probability is a number from 0 to 1. 0 indicates impossible or unlikely, something unlikely to occur. A probability of 1 will indicate almost certain or certain. And then a probability of 0.5 indicates occurrence of the event is just as likely as it is unlikely. Okay, so I'm just giving you a basic intro of probability. So let's say if I have this scale with me from 0 to 1, where 0.5 is the middle number of 50-50 chance. Let's say I have 0.1 as a probability here, 0.1. So what will 0.1 indicate as a probability? And if I have a probability of, let's say, 0.9 in a situation for an event, what will that mean for us? Okay, so when a probability is pretty close to 1, okay, that's more likely to happen. So anything above 0.5 is more likely to take place, and anything below 0.5 is less likely to take place. So any number which is close to this 0, the chances are that it's not going to happen. And if a probability is high, close to 1, then the chances are there are good chances that it will happen. Okay, there are very good chances that that event will occur. And when we say event, so naturally there is something that will happen in future, or maybe that we are not a part of. We can calculate the probability for it, and we can say that, okay, these are the chances. So events, I will come to events a bit later, and experiments and all that stuff. But just try and understand what is probability. It's a number from 0 to. So probability can never be below 0, and probability can never be above 1. These are rules for you. You have to remember them. Okay, let's go to the next slide then. Okay, so what is there on? Let me just first erase this these numbers from this scale. Okay, so let's just go to our next slide. Okay, so how can we assign probabilities? How the assignment of these probabilities can take place? So naturally, we have to follow some rules here. There are a number of methods using which we can frankly compute probabilities, like the classical method, which is the oldest method. And this is basically, it has an assumption of equally likely outcomes. I'll come to this with some examples. Now, the first is the classical method. So that's the oldest school of thought. Then came the relative frequency method with progress in our data collection and data storage methods, and especially the invention of computers, and now the large resource of data storage, where you can put your data on clouds or you can put it on your gadgets. So there's a lot of storage that you can have. So most of the organizations these days, they collect data and they store data, and they have that data for their analytics. So big data analysis has become a very important new area of research and statistics these days, where a lot of digital data is being analyzed for different purposes by businesses. So that is the relative frequency method, where historical data, whatever is recorded, is used in computation of probabilities. But please remind yourself that I taught you how to calculate the relative frequency table when we were discussing the frequency distribution of the frequency tables. So that's the same concept. I mean, you have to take the individual frequency and divide it by the total frequency to get the relative frequency. Relative frequency is also called the probability. I think I told you this when we were discussing this, even in that section. The third is the subjective method. This is also called the Bayesian approach to probability. In this, historical data and common sense both are used. The judgment is also used um, in computing probabilities. So human judgment or human intuition or human understanding, a human's understanding of a situation plays a vital role in giving probabilities in the subjective method. This is just like, at times you must have seen physicians, when you visit them, they give you the best chance of a particular disease that you or your loved one might have. They tell that from their experience, and many of the times they're correct. Okay, so that's the subjective method uh, or the Bayesian method that you're using. So we'll be discussing each one of them in detail. Let me go ahead with the presentation. So what is the classical method? In the classical method, if you see, there are different things covered. You can see experiments, you can see the counting rules and the assignment of probability. So in classical method, frankly, there's a lot of theory involved. And I guess at times, this is what I've seen from my previous experience, that most of the students are stuck here. They do not understand fully the concept of experiments and then the counting rules, especially. Event and their probabilities, they become relatively simpler, and then the relationships or some laws of probabilities are discussed, then the conditional probability and the Bayes theorem. So these are the topics that are covered in the classical method. Bayes theorem is like a conditional probability theorem. We will see when we are there. That's a very important application in real life. Okay, so now what is our experiment? The first topic here was the experiment. What is an experiment? An experiment is such an activity that generates a random kind of outcomes for us. Though we may know the possible outcomes that they may generate, but I mean, under essentially similar conditions, if we repeat them, if we put them to trials, the kind of outcomes they generate, we can't be sure of them. So this is just like tossing a coin. If you toss a coin, you can get a head or a tail. So there are two possible outcomes, but you don't know for sure which outcome you will have. It's only the likelihood of that outcome that you're interested in. So maybe if you're saying, okay, what is the likelihood of the head to occur? How likely is the head to occur? So because there are two outcomes, the probability theory says that there are two outcomes. One of them is favorable to head. So 1/2 is the probability. 50% chance that it will be a head and 50% chance that it will be a tail. Similarly, if you're selecting a part for inspection, if you are in your production house and you're in the store where the product was randomly put, you select a part for inspection. You don't know whether that is defective or not defective. So there are two outcomes possible again. So again, it depends that, what is, if you look at the historical data, maybe the chances are different, but if you're looking at only the two possible outcomes, the chance of defective may be 0.5. Similarly, if you're conducting a sales call, maybe somebody purchases or there's no purchase. If you roll a die, you get 6 outcomes. If you play a football game, you win, lose, or tie. If you start a business, maybe there's a profit, break-even situation, or a loss. Okay, so these are different experiments in life, and They generate a different kind of experimental outcomes for us. Okay, some of the experiments are also discussed in the book. You can go and you can watch them, you can read about them. Okay, so an experiment and its sample space. Now, these are technical terms. Okay, I just told you that experiment is a process that generates well-defined outcomes. Okay, like in the case of a die tossing, we had 6 well-defined outcomes, 1 to 6. Okay, and one trial if we do, I mean, once if you roll a die, you may get a single number turning up. Okay, so that's a single trial that you're doing. You can do many trials. Okay, you can do 2 trials or 3 trials or many trials. But imagine the sample space. What is the sample space? The sample space is frankly the total space that an experiment will generate for us. So in the case of a die, if we roll a die, okay, a die is tossed. Yes, this is a die. So what are the outcomes? The outcomes will be, usually we write it in set form. So that's 1, 2, 3, okay, and then 4 and 5 and 6. Okay, these are the 6 possible outcomes. They're all well-defined outcomes, but which of these outcomes will come up, we don't know. So this thing is called the sample space. The sample space is the space where from a single result can emerge for an experiment. Okay, so if we say that, okay, what is the chance of 1 to appear? So I mean, if we look at the classical definition of probability, the definition actually is, I'll be discussing this later as well, but we can write it. Usually probability is denoted by, the events are denoted by capital letters. So I'm writing probability of A, where I'm just saying that, okay, what is the probability of an even number to appear? How many total numbers do I have? I have 6. So there are total 6 outcomes that can take place. So usually the total outcomes are in the denominator. And if I say, what is the probability of an even number? How many even numbers in my space are there? 2, 4, and 6. Okay, so I have 3 outcomes favorable to the event that I'm posing. The event was the probability of even number. So I can write this as probability of A, or I can write this as probability of even number. So this is the probability of even number. Okay. Okay. Even. So this is even, EVEN is equal to probability of, and favorable are 3. So usually the favorable outcomes are denoted as M, okay, and the total outcomes are denoted as N. That's the definition of classical approach to probability. So the total outcomes were 6, favorable to even were 3, so the probability of even is 3 by 6. So you saw that I discussed an experiment here. A die is tossed, sample space for it, 6 outcome. Usually S is the sign for denoting a sample space. S is equal to this sample space, and you write it in a set form. A sample point is an element of the space. So every single unit here is a sample point. Okay, I hope you get this. Okay, now if we say that, okay, let's do it for another experiment. Okay, let's say another experiment is toss a coin. So if we toss a coin, you know that there are going to be 2 outcomes. So the 2 outcomes are heads and tails, and these heads and tails, they can be taken as a sample space. So S is equal to, okay, the total outcomes are 2 and they are heads, and tails. Okay, please remember that I'm tossing a single coin. So how many total outcomes do I have? 2. Okay, and if I ask what is the probability of a head, okay, before I toss the coin or during we toss the coin. So what is the probability of head? Actually, head is 1 in the total space. It's just 1 point, 1 sample point. So m is equal to 1. Actually, m is equal to 1. Okay, so 1 by 2 will be the probability. So this is how you calculate probability with these simple experiments. Now, let me take you to some more examples using the and some more experiments in the classical definition of probability. Actually, I have a few simulators downloaded already. So let me just show you that. Okay, I'll have to share that first with you. So let me just share that with you. Okay, so you see here I have a single coin. Okay, if the 0 and 1 indicates the head and the tail. So imagine if I flip it once, there has to be an answer. So either head or a tail. So just look at the simulator how it goes. I've set a single coin here, and the chance of heads is 0.5. Now this is important because the classical definition of probability assumes equally likely outcomes. Equally likely means that head and tails are equally likely. Okay, they have the same chance to appear. Sometimes this can happen that a coin may be unbiased. Sorry, a biased coin. So a biased coin may have heads appearing more likely compared as tails, but we are not discussing that right now. We are assuming that all the outcomes are equally likely. So if I flip it once, just take a look. See, I get a tail. So I got a 1 against a 0. If I flip it again, I got a tail. Because this is random, let me do it 10 flips. So I'm putting it to 10 trials. Now, can you see 7 tails and 5 heads out of the total 10 flips I gave it and 2 flips I had? So 12 outcomes totally. Let's do it auto. Auto means that this will run indefinitely for huge number of trials. So I will just stop the flips whenever I feel to stop them. Okay, so just take a look. In the auto, can you see the flips are increasing, and look at the number of heads and tails. Now, one thing is important here to be learned, that when the flips are too many, you will see that the number of heads and the number of tails, they will come pretty close to each other. And that is our definition of equally likely. That heads, I mean, in the long run, any coin should show us that heads and tails have the same chance to appear. Now can you see on 1,000? Can you see there are almost 500, both of them? Okay, so let me just stop it. Okay, and just take a look at it. So can you see 655 times tail came and 702 times a head came? Okay, there are statisticians who have done this actually 60,000 times, these flips, and they've gotten almost equal number of heads and tails. But this was for a single coin. Okay, let me take you to a dice roller now. Now in this experiment, I'm sure you have played Ludo at home. I'm just taking a single die here. This is a single die. I just gave you this example in the slides as well. Okay, if I roll the die, from 1 to 6 some number will appear. Okay, roll the die, I will get a random number here. Now can you see I got 1 again? Okay, so what is the probability? What was the probability of this one? There were 6 outcomes, and this one is just one number out of those 6. So the probability was 1 by 6. So if every number appears with a 1 by 6 chance. Okay, If I ask you what is the probability of an even number, an even number has a probability of 0.5 because there are 3 even and 3 odd. Okay, now let me just write this again for you. In our sample space, if you recall, we had 6 outcomes. Sorry about this 3, I can hardly write it. Okay, 4, and then 5, and then 6. Okay. Okay, let me just roll this die again. Can you see 6? Now, because this is an even number, the chance was 50%. So naturally, I will get one of these numbers. Okay, so we can have different probabilities here. What is the probability that a number 2 or below will come? Okay, what is your best guess here? What is the chance that a number below the chance for a number, let's say the number is x, less or equal to 2. So less or equal to 2 will come. So how many numbers do you see here are less or equal to 2? Actually, these 2 numbers. So what is the chance for it? Total outcomes are 6. Okay, I have the total outcomes to be 6, and the favorable outcome for my event is 2. So what is going to be the probability? 2 by 6 or 1 by 3. So 2 by 6 or 1 by 3 is actually 0.33, 0.33. Okay, so let's roll it again. Let's see, this is less likely to happen, but still it can. Okay, so it is less likely, but let's roll the die again. You saw the number came out to be 3. More likely was a number 3 or more because this had more outcomes to support it. Okay, so similarly, there are other experiments that we can see here in our list. Let me just show you those. Okay, there's a famous roulette game, usually that is played in the casinos around the world. That's not a very good example usually to give, but but probability theory again looks at it, and it can frankly gives us a lot of understanding in understanding the basic stuff of probability. Okay, so this is the roulette, and in the roulette, if you see, there are the inside numbers and the outside numbers, and there are rules for it. Roulette is basically a wheel that has 36 numbers, and there's a number or two for the casino. I mean, the European casinos, they have a single number where they will win it, and the American casinos, they have 2 numbers. So in the American casinos, you may have 36 numbers, not numbers, numbers, because they put a 0 and 00 in there, and in the European you have 37. Okay, but the numbers on which you will bet is going to be where you can win. So these numbers, you can bet on them. Like you can see, I can bet different value on them. So let me bet $100 on something. So on the inside numbers, if on a single number, if I'm betting, I will get 35 times of that return. So imagine if I'm putting $100, okay, I will get $3,500 if I win. Okay, but the chance for that has to be low. If I put my numbers on red or black, now because half of them are red and half of them are black, there's a 50-50 chance that I win or lose. So if I win, I double my amount. So if I put 100 rupees here or $100 here, if I win, I will get 200. Okay. Similarly, there are many rules in there, but let's just see. Let's just play this. Okay. So what should be? Where should I have the highest probability to win? So naturally, I can put on odd numbers or even, because odd and even um, are, are randomized. I can put my bet on the first 12 numbers. I can put my bet on the 19 to 36 numbers, 1 to 18, or something like that. So let me bet on 100, the 100 on red, and let's play the game. Now, what are my chances? My chances are 50-50 to win or lose. Okay, let's just spin the wheel. Red. Remember, my bet was on red. I won the game. I've doubled my amount. You can see that 100 was invested, and now 100 more has come. So I've earned some money here. Okay, so a roulette has another application of probability. We can frankly think of applying this. Okay, now let me show you another experiment, which is of the cards experiment as well. Okay, so the last one is of the cards. I'm sure you've seen the playing cards before. So I think I've given the picture of playing cards on my account as well, on my Google site as well. So let me just share a picture with you, playing cards. Okay, it's a picture upload. Yes. Let me just share this with you. Okay, so just take a look at this picture, and hopefully you can understand more about the cards. So there are 4 suits in cards. Okay, and you can see that half of the cards are red and half of the cards are black. Now, probability again will consider that, if I'm drawing a single card out of these 52 playing cards, or if I'm drawing more cards, like 2 or 3 or 4 cards or 5 or 10 cards maybe. Okay, so let me take you back to the simulator. You can see that there are spades, hearts, diamonds, and clubs. So what are spades, hearts, and diamonds and clubs? You can see that these are hearts and diamonds, and these are spades and clubs. Okay, so spades and clubs are black, and hearts and diamonds are red. At the same time, you can see that there are 12 cards having pictures in them, like the jack, queen, and king. They have pictures of it. This is important information for computing the probability in different contexts. Okay, so let me take you to the simulator. We will simulate one card from the 52 playing cards. So let's just do it. Let's draw a card. It will draw out a random card, and you saw it's a black card. Now, what was the probability of a black card to come out? Because the total cards were 52 with us, okay, I had in total 52 cards. Okay, these cards are 52, 13 suits of each, so that's like 13 into 4 is 52. And black, how many black cards were there? So black were actually 26. Okay, and how many are red in our cards? So red are 26 as well. So what will be the chance of a black card or a red card? So the probability for a black card would be naturally 26 by 52. Okay, so 26 by 52 will be 0.5. Okay, that's I'm just dividing the favorable outcomes. These are my favorable, and the total outcomes. These are my total. So I got 0.5. And what is the probability of red card? Now the probability of red card is, the probability of red is again 0.5. Okay, so this is how we can easily compute the probability for any random event that we may think of. So let's do it once more. Let's run the simulator once more. Because the chance is 0.5, you can see now I'm getting a red card. So the chance is very high for both of them, equally likely indeed. Okay, so just keep on doing it, and you can see that this can very easily do the job for us. Okay, now let's take another situation here. Let me show you the cards again. If I ask you a question, what is the probability for a heart card to appear? Okay, now how many heart cards are there with us? We have in total, I told you there are 13 in each suit. So there are 13 here, and there are 13 here, and there are 13 with the next suit, and 13 with diamonds. Okay, yeah. So I have 13 heart cards. So this is my favorable number of outcomes for a heart card to appear. And what are the total outcomes? The total are 52. Okay, so what should be the answer? Actually, the answer should be the probability of a heart card. Okay, we can denote it by ABC. So you can write A, A denotes a heart card, and you can write it as equal to 13 by 52. Okay, okay. Now this 13 by 52 is actually 0.25. So the chance for a heart card to appear is 0.25. That's less likely to happen. So let's run the simulation once more and see. But still, it can happen. Okay. So what is the probability of a heart card? Let's do it again. The chance is 25%. You saw it's not a heart card. It's another card. Let's do it again. Still, you see, because it was less likely to happen, the heart card is not coming out. This time it came. So after a few trials, you may see. So what we expect is that out of 4 trials, perhaps once it should be a heart card, because that's the natural probability. I mean, not necessarily, but this is how it should be. Okay. So this was little example with the card. So usually you see the experiments of these roulette or the cards or the die or the coins. We can increase the number of coins. We can go for 2 coins maybe. Okay, and then we can auto flip it. Now you see if there are 2 coins, let me just explain this. 0 means both are showing you tails. 1 means one is showing you head and one is showing you tail. And 2 heads means both are showing you heads. Now you can see a head and a tail is giving you a higher frequency because that is more likely to happen. Okay, 2 tails and 2 heads are less likely to happen. Okay, so that is why their chance is a little low. And why is that? Just let me just explain this a bit further. Okay, so take a look at the, sorry about this, chose the wrong thing here. Okay, so let me just pick a pen. Okay, so when we toss 2 coins together, the sample space is usually of 4 outcomes. I can have heads or a head. Both the coins are showing me heads. That's possible. That's scenario number 1. I can have a head tail. The first coin shows a head, the second a tail. Okay, and I can have a tail head. The first shows a tail, the second a head. Or I can have a tail scenario. Okay, a tail scenario. Now, if I ask you, what is the probability of 2 heads? That's naturally 1 by 4. 1 out of 4 is the probability for 2 heads to pair. What is the probability of 2 tails? Just one situation out of 4, 1 by 4. But what is the probability of a head or a tail? Naturally, this is 2 by 4. That's more likely. So that is why you see more frequency for a head and tail when you auto flip the experiment. Okay, you can see if I auto flip it again, they keep on rising, but they will maintain this natural relationship that, uh, most of the times you're going to get these results compared to the 2 heads and to the 2 tails. Okay, so let's go back to our presentation. Explained a few basic things in there. Now, just imagine I was talking about the experiment, sample space, and the sample point in all of those experiments. You can read the book and you can try and understand the concept better. Well, this example is about an investment idea. Bradley has invested in 2 stocks, in the Markley Oil and the Collins Mining. Okay, and they have determined the possible outcomes there. So Markley Oil has 4 possibilities and Collins Mining has 2 possibilities of gain or loss. When you're in the stock markets, usually this kind of data is very easy to find. Your broker or the account that you're maintaining can give you that kind of information. Okay, but with Markley Oil, if you see as a possibility, 1/4 possibility of a huge loss and a 1/4 possibility of making a 10% return. With Collins Mining, there are just 2 outcomes. A low chance of losing some money. I mean, an equal chance of losing $2,000 and a 50% chance of making $8,000. Okay, so you are actually so let's take a look at how these possibilities will frankly result. But before we do this, there's a counting rule that I want to discuss. That if you have a multi-step experiment, like in this, if you can see that these are like 2 experiments mixing up. One is Markley Oil and the other is Collins Mining. Like in our case, this was perhaps a single coin, and now there's another coin in place as well. So there are 4 outcomes that are emerging from the first, and there are 2 outcomes that are emerging from the second. So in statistics or in probability, if you want to see the total outcomes, so N1 is usually from the first experiment. How many outcomes do I have? I have 4 outcomes. And N2 is the number of outcomes that I have from the second experiment. So these are 2 outcomes. So according to the law, if you want to combine these 2 experiments, the total outcomes are going to be N1 into N2. And this is called the multiplication law of probability, okay, of counting actually. So this is 4 into 2. So this will give us 8 outcomes. Now, how would we think of these 8 outcomes? Okay, the 8 outcomes could be that this. I mean, let's say you're the investor. You invest in both these possibilities. So it is quite possible that you get a 10 return from this one, but you get an 8 from the second, and likewise 8 from this one, but a -2 from this one. So these become 2 possibilities, 10, 8 and 10, -2. Similarly, the first can result as 5, and then an 8 and 2 can come. Similarly, 0 and 8 and 0 and -2 can come, and -20 and 8 and -20 and -2 can come. So the worst scenario for Bradley would be -2 and -20, because if that happens, Bradley will be losing a lot of money, -20,000 in Markley and -2,000 in Collins Mining. This is what he doesn't, or she, I don't know, Bradley, whosoever it is, would not like. The liked scenario would be 10 and 8, that she makes 10 from Markley and 8 from Collins. Okay, so let's proceed. There's another way of looking at this as well, and that is called a tree diagram. So I'll be explaining that again. That's a very simple kind of a diagram that you can make, because I just told you that there are 4 possibilities here and 2 here. So let me just do it at the same place so that you understand it. Okay. Yeah, let me get a pen first. Yeah. So if there are 4 outcomes from Markley, so my 4 outcomes. Okay, let me re-choose another color because I can't show it on the back side. Okay, so yes, and where is the color? Yes, here is the color. Okay, let me choose a red. So there are 4 possibilities for Markley oil. So possibility number 1, 10. Possibility number 2, 5. Possibility number 3, 0. And possibility number 4, minus 20. So let me just write those here: 10, 5, 0, and minus 20. Okay, these are the 4 possibilities that can happen with the first investment. And then 8 and minus 2. So, after this 10, if we make just 2 more branches with 8, okay, with this 8 and minus 2. And we repeat this for all the branches. With 5, you get 8 and minus 2, okay? And with 0, you get 8 and minus 2. And with 20, you get 8 and minus 2. Now this becomes a tree diagram. So what are the possible outcomes that can happen? 10 and 8 is the first outcome. 10 and minus 2 is the second outcome. 5 and 8, third. 5 and minus 2, fourth. 0, 8, fifth. 0, minus 2, sixth. Minus 28, seventh. And minus 20, minus 2, eighth. So there are 8 possible outcomes that can happen for us. Okay, so let's just go to the next slide. Okay, let me erase this first before we move on. Okay. Okay, so this is what I just told you, that the counting rule is that you have to multiply outcomes of the first experiment with the second. I mean, if there are more experiments, 3 experiments or 4, and if you're taking them together, then you can actually multiply the outcomes of each one of them together. Similarly, a tree diagram can help us as well. This I just explained to you along with this tree diagram as well. So you can see that these are the possibilities. So you can see that there are 2, 4, 5 possibilities of gain for Bradley and 3 possibilities of losses for Bradley. Okay, now this is the complete scenario of investment. Okay, now another useful rule of counting that comes for outcome counting is the combination rule. Now, before I discuss the combination and the permutation rule, let us just go back and then do a few problems, perhaps on the concepts that we have learned so far, so that we are good with it. So I'm just breaking it down here, and let me just show you. Let me take you to the book, and let's solve a few problems there. Okay, let me just give me a second so that I open the book for you. Okay, yeah, it should take a couple of seconds. Not this, sorry. Yeah. So I'm showing you the book here. Okay, take a look at the book. Now I'm on chapter number 4. I gave you the basic concepts. Okay. So let's quickly do a few problems there. Okay, let me just drag it back to the, yes, to the main page. Yeah. So section 4.1 I was discussing with you. Okay. Let's get to the first exercise. You will read this carefully, and if you will have any questions, ask me, please. Okay. Now these are some simple questions that you can do, and you can think about solving them yourself. Okay. An experiment has 3 steps. So let's do question number 1. An experiment has 3 steps with 3 possible outcomes for the first step, 2 for the second step, and 4 for the third step. You just saw a multi-step experiment using the multiplication counting law. Okay, so that's you can do it either using the total outcomes, or you can do it using the tree diagram. So 3 steps, 3 outcomes for the first step. These are the 3 outcomes for the first step. You can say outcome 1, outcome 2, outcome 3, and 2 for the second. So after this, you have 2 for the second. That's 2 for the second from each of the previous branch. And then finally, 4 for the third. So from each branch, further 4. It's like 1, 2, 3, 4. Similarly, 1, 2, 3, 4. And this is 1, 2, 3, 4. This is 1, 2, 3, 4, and so on and so forth. 2, 3, 4. I'm not having enough space actually here. You can do it yourself. But what are the total outcomes? So I had 3 in the first step, multiplied with 2 in the second step, and 4 in the last step. So how many total outcomes should I have? That's like 24 outcomes. There are 24 outcomes. That's your first answer. So you're just counting the total outcomes here. You can count it like this. The first outcome is this first branch. The second outcome is the second branch till the end. And then this third branch, and so on. And so if you count them, they're 24. Okay. Okay. Similarly, you should apply yourself to some of these simple questions. Very easy. It should not be a big trouble for you. Okay. Okay. Okay, question number 7. Let's see question number 7. What does it tell us? It is saying that a decision maker subjectively assigning the following probabilities to the 4 outcomes of an experiment. So the first is 0.1, 0.15, 0.40, and are these probability assignments valid? So how can we check this? So please remember, the first check is that are all probabilities in between 0 and 1. So any probability should be a number from 0 to 1. So yes, they are. That's the first check. So in that respect, they're all right. Okay. But then the second is, for any experiment, the total of the probabilities has to be equal to 1. So if I sum up all the probabilities, okay, I should have, if I sum up all the probabilities, I should have 1. So do I get a 1? 0.1 and 0.25, and this should be 0.65, and then 2, 0.85. So they're not valid because there's another probability missing here. Okay, there has to be a probability of E5, something which is missing here. Okay, so that's they are valid, but one of the outcome or event is missing here actually. Okay. Okay, so let's just stop for a while, and I'll be back with further explanation on the same topic. I'm a little tired now, so let's just stop this and I'll see you in the second lecture on probability.